Hi, we will be discussing this project risk assessment based on this experiment. This experiment involves the free radical bromination of 2-chlorotoluene using bromine in carbon tetrachloride under photochemical irradiation, which is 500-watt lamp. And the reaction mixture is reflux, wash, and purify by evaporation and vacuum distillation to yield 2-chlorobenzyl bromide with 80% of efficiency. Moving on, this slide shows the NFPA hazard diamond, which is used to indicate the risk associated with hazardous materials. The first one, blue section, represents health hazards, ranging from normal materials to deadly substances. The red section, it indicates fire hazards, showing how easily a material can ignite. For yellow section, it shows instability, meaning how likely a substance is to explode or react. Last one, white section, it lists out the specific hazard, such as corrosive materials, oxidizers, or substances that should not be mixed with water. This slide shows the overall hazard ratings of chemicals used in our experiment, which based on the NFPA diamond system. So we have 6 chemicals. The first one will be tetrachlorocarbon, bromine, hydrogen bromide, sodium bicarbonate, 2-chlorotoluene, and 2-chlorobenzyl bromide. And the most hazardous would be the bromine, which is highly toxic, corrosive, and a strong oxidizing agent that can intensify fires. And in contrast, sodium bicarbonate is a low-risk, non-flammable, and chemically stable, which only causing minor irritation.
Okay, next we move on to specific safety measures. So for our safety measures, we are focusing on two main areas. First one is engineering controls and PPE. So the first one is fume hoods. We use this to safely ventilate any respiratory hazards. And next one is emergency infrastructure. So this includes easy access to fire extinguisher. And the next one is PPE, which everyone must wear a lab coat, safety goggles, and protective boots at all times. The next one is major hazards of experiment operation. During the operation of this experiment, there are two primary risks to watch out. The first one is vapor escape. So if the condenser fails, it can allow flammable or toxic vapors to escape into the lab. The next one is risk of implosion if it has any micro cracks. So because we are using a vacuum setup, any small micro cracks in the glassware could cause an implosion. So we must inspect all equipment before starting.
For this slide, I will explain the major chemical hazards involved in this experiment. Hydrogen bromide gas produced during the reaction is corrosive and can form acidic fumes that irritate the respiratory system. Bromine is highly toxic, corrosive, and volatile, can cause severe burns to the skin and eyes, and inhalation of bromine vapor may lead to serious respiratory irritation or lung damage. Tetrachlorocarbon can cause liver and kidney damage. The product, 2-chlorobenzyl bromide, can act as a strong irritant and lacrimator, causing irritation to the eye, skin, and respiratory tract. This slide explains why these hazards are particularly important in this experiment. Bromine is used in a photochemical reaction under UV light, which increases its reactivity and the risk of uncontrolled reactions or vapor release if not carefully added. The use of tetrachlorocarbon as a solvent increases inhalation risk due to its high volatility and toxic nature, especially during reflux and solvent evaporation under reduced pressure. The formation of hydrogen bromide gas further increases the risk of corrosive fumes during the reaction and walk-up stage.
Hello, my name is Nurul Shahada. I will briefly explain the emergency response procedure and chemical waste disposal for bromine and tetrachlorocarbon. First, bromine is highly toxic and corrosive substance that can cause severe burns to the skin, eyes, and respiratory tract. In case of skin contact, contaminated clothing must be removed immediately, and the affected area should be rinsed with plenty of water for at least 15 minutes, followed by medical attention. For eye exposure, the eyes should be rinsed continuously with running water while keeping the eyelids open, and urgent medical help must be sought. If bromine vapor is inhaled, the person should be moved to the fresh air immediately, tight clothing loosened, and medical assistance sought if breathing becomes difficult. In case of ingestion, vomiting must be induced. Instead of the mouth should be rinsed with water and medical help sought immediately. Next, tetrachlorocarbon is a toxic and carcinogenic solvent that can damage the liver and kidneys. If inhaled, the person should be moved to the fresh air and medical attention should be obtained if symptoms such as dizziness and nausea occur. If skin contact, the affected area should be washed thoroughly with soap and water, and contaminated clothing should be removed. In the event of chemical spill, the area must be evacuated immediately and appropriate personal protective equipment should be worn. Small bromine spill can be neutralized using sodium thiosulfate and absorbed with inert material, while large spill must be reported to the laboratory supervisor and handled accordingly to the institutional emergency procedures. Although the bromine is non-flammable, it is a strong oxidizer. Therefore, in the case of fire, heat sources should be turned off, appropriate fire extinguisher used, and evacuation carried out if the fire spreads. Finally, chemical waste must be disposed of properly. Bromine waste should be neutralized before disposal as halogenated hazardous waste. Tetrachlorocarbon must be collected in labeled containers, and organic residues should be clearly labeled and disposed of according to laboratory guidelines. Thank you.
For the conclusion, this experiment successfully demonstrates the photochemical bromination of 2-chlorotoluene to produce 2-chlorobenzene bromide under real flux condition. Second, this experiment involves significant chemical hazards, particularly from bromine, carbon tetrachloride, hydrogen bromide gas, and the brominated product which are toxic, corrosive, and irritating. Also, proper neutralization and disposal of chemical waste are necessary to prevent environmental contamination and health risks. Furthermore, operational hazards such as high-intensity UV irradiation, heating under reflux, and vacuum distillation increase the risk of vapor release, pressure buildup, and gasware failure. Strict safety measures are essential, including working in a fume hood, wearing appropriate PPE, controlling the rate of bromine addition, and allowing the reaction mixture to cool before workup. Overall, this experiment emphasized the importance of risk assessment, hazard control, and safe laboratory practice to achieve both effective results and laboratory safety. That's all for us. Thank you for your attention.